Hello, my name is Josh Speck, and I'm going to go through section 1.6 from our textbook, which is about knots and sticks. So just to kind of give you an overview of what we're going to talk about, first thing is we want to decide just how many sticks do we need in order to make a knot. So what is our minimum number of sticks required? Then we're going to look at one of our very well-known knots, the trefoil, and look and see how we can make this out of sticks and does it actually work. Then we'll move on to defining the stick number, which is the invariant that is discussed in section 1.6. And we'll work a couple of exercises as we go, and we'll end with some unsolved questions involving sticks and also talk about a couple of applications. So to begin with, we want to know, what is the minimum number of sticks required to make a knot? And so to begin with, specifically, I should say, we want to know how many sticks does it take to make a non-trivial knot, not just the unknot, but an actual knot. So as we could probably guess, 3 is not enough. The only thing you can do with 3 sticks is make a triangle. But what can we do with 4 sticks? And one of the first exercises in this section asks us to prove that we can only make one crossing if we have 4 sticks, that one crossing is the most we can make. So to illustrate this, what I'm going to do is I'm going to go here to GeoGebra. This just seemed like kind of a nice way to illustrate this. And basically what this proof comes down to, I'm going to do it visually as opposed to trying to write something out for you. Basically what we're going to show is that any one of these sticks can really only cross a stick that it is not connected to. So for example, I can only make stick AB cross stick CD because it is not directly connected to stick CD. Okay, I cannot make AB cross AC. I cannot make it cross B. The best I can make it do is overlap, and that's not really going to fly. It's not a knot. And I can't make it cross AC for the same reason, because again, but I can make it cross stick CD, and I can, make it cross anywhere along CD that I want, but that's the only stick that I can make it cross. And the same is true for all the sides. The only stick that I could make BD cross would be AC. I can bring point B over here, or I can bring point D over here, but the only eligible stick to create a crossing with for any particular stick that you might want to decide, all right, this is the one I want to cross another one, the only eligible stick is the one straight across from it. So at most, you can have one crossing because there's only one eligible stick that you could make a crossing with. So furthermore, let's note that if I've already created one crossing, okay, so here I've got my crossing occurring between sticks AC and BD. If I try to make a second crossing, so the only 2 sticks that are eligible now would be AB and CD. If I try to make a new crossing with these sticks, notice that I can't do that without undoing the first crossing, right? In order to make a crossing, I either have to bring D up here like that, in which case now this crossing isn't happening anymore, right? The one between BD and AC. Or I have to bring this one up, right, in order to make CD cross AB. And I can't do that without undoing the first crossing. So I'm limited here to only one crossing between opposite sticks. That's the general idea of proving this. I think the visual effect of showing the only stick that you can make a crossing with is the opposite stick is maybe a little more powerful than trying to write something out. So that's the idea behind exercise 132. The book also references this idea that you were born with 5 sticks, quote unquote. If you count your hand to your elbow on one arm, up to your shoulder, and then across both shoulders, and then down the other arm and down your forearm, you have 5 sticks. And the author challenges us to try to make a knot with just our 5 sticks. And I thought about making a short video where I have my kids try to twist their arms around, and they just weren't into it. So the author suggests that we don't try too hard because we'll hurt ourselves. It really can't be done. So the conclusion is that you need at least 6 sticks in order to make a non-trivial knot. So what we could do perhaps is take something like a ruler or a yardstick or something and hold it between our hands and try to cross our arms and the yardstick to make a non-trivial knot. We are, of course, limited by the joints of our elbows and shoulders and whatnot, but theoretically, you could perhaps make a knot with your 5 sticks and your yardstick. But let's talk about what we know to be the simplest non-trivial knot, the trefoil, and I've put a little asterisk here just to be kind of humorous, because now, of course, we know that there is no the trefoil. It is a left-hand trefoil and a right-hand trefoil, but if we were still in section 1.6, we would not know that yet. So the book kind of challenges us, the textbook challenges us to verify that this really works. Here we have a projection of the trefoil, of a trefoil that is made out of sticks, and we need to verify that the sticks are truly straight. Just because they don't curve in the plane, right, does that mean that they are still straight in 3 dimensions? Are they actually straight sticks? And so there's a couple ways that we could verify this. We could use real sticks, of course, toothpicks or popsicle sticks or something of that nature to show that they really do work and they are not being bent and curved in any way.
Okay, so here's my take on the trefoil made out of sticks. I basically used some popsicle sticks and stuck a little bit of Play-Doh on the ends to kind of hold it together. But you can see that all my sticks are in fact straight. I would pick it up and try to show you different angles, but it's entirely too fragile for that. So hopefully just some kind of angled shots like that will show you that this is in fact the trefoil knot made out of entirely straight sticks.
The textbook itself gives a pretty convincing argument that if you assume that these points here labeled with a P are in the plane, and then points labeled with an H are above the plane, they are high points, and labeled with L are below the plane, those would be low points, then we can verify that the sticks actually cross in the way that is shown here with the undercrossings and overcrossings, and it actually does work. There are no curves. All of these sticks are indeed straight sticks. So now beyond that, as we get more complicated knots, we want to know, how many sticks would it take to create a particular knot? So for example, the figure 8 knot, right? The figure 8 knot is the next most complicated, I guess. It's the next number of crossings that we have, the 4-1 knot as it's labeled in our table in the back. And it turns out that it requires 7 sticks to make the figure 8 knot. So to kind of illustrate that my projection does work, we'll start with a fairly familiar projection of the figure 8 knot and kind of see how it transitions into the stick knot. Notice that this stick knot has 7 sticks, and all of the crossings in the stick diagram are in relatively the same positions as the sticks in, not the sticks, I'm sorry, in the regular projection of the knot. So we can kind of follow along with both projections and see that they are in fact the same. One of them just has straight lines. Next, we want to discuss the stick number. This is the invariant that's mentioned in section 1.6, and it has a really simple definition. It is kind of by definition an invariant, similar to the bridge number, right? Where the bridge number is defined as being the least bridge number of all projections. The stick number is defined similarly, right? It's the least number of straight sticks necessary to make any particular knot. So by definition, it's an invariant, kind of like the bridge number. So one of the things that we would like to show regarding the stick number involves compositions. We did some work with compositions early in the text. We want to show that the stick number of the composition is at most one less than the sum of the stick numbers of the two factor knots. So this is something that I'd also like to illustrate with GeoGebra.
So for the purposes of this illustration, I have two knots, and the particular knots that I've chosen are not important. What's important is the method that I'm going to use to compose these two knots. But for the sake of just having a good, hopefully a good illustration, I'm using the trefoil knot here on the top and the figure 8 knot on the bottom. And what I want to do is I want to identify a couple of corners that I'm going to use to connect these two knots. So in particular, I want a corner that has a segment attached to it, a stick attached to it that is an outermost stick. If you remember when we did composite knots early in the course, we needed an outer loop on each knot to compose, and we used two straight lines to compose the knots. So here we need outer loops. So really what we're going to do is we're going to focus on a corner and a stick that is on the outside, right? It doesn't cross anything else. It's sort of an outer stick. So I'm going to use CD and GH. Those are going to be my outer sticks for the trefoil and the figure 8 knot, respectively. And what I want to try to do here is I actually want to go ahead and link up C and G. Okay, but I have to be careful to do that in such a way that I don't really change my knot. So I'm going to try to make this knot continue to look like the figure 8 knot that we, figure 8 knot that we know. So that's pretty good. So basically, at this point, we don't have a knot, right? We've joined these vertices up, but no knot that we've ever dealt with has 4 strands going into one crossing there, right? That's not good. So basically what we want to now do is we're going to get rid of one line segment from the trefoil knot. We're going to get rid of CD. And I could do this either way, but I think this is going to be the easiest one to illustrate this with. And then I'm going to take this line segment, and instead of having M connect to G, now M is going to connect to D. So I need to get rid of that, and I need to redraw here. So I've eliminated one stick from the trefoil knot and reconnected the end of the stick that I deleted with the previous vertex, I guess we could call that, of the stick that was joining it. So I'm not sure verbally that I'm saying that very well, but hopefully the visual makes sense. We connected at a corner, and then we deleted a stick from one of the two knots and reconnected here. So now every point has 2 sticks connecting to it, right? Which, if we follow the path of for a knot, if we just pick a point, like say we pick A to begin with, and we follow this around, we see that we have one continuous looped knot. So again, the particular knots, the trefoil knot and the figure 8 knot, are not important. What's important is this idea. We connect their vertices and then eliminate one of the outer sticks on one of the knots and reconnect the stick that was going to this corner, one of the 2 sticks that was going to this corner, we reconnect it at the other end of the stick that we eliminated. So we can see that we didn't change the number of sticks on the figure 8 knot, but we reduced the number of sticks by 1 on the trefoil knot. So the total number of sticks is now 1 less than the sum of the 2 stick numbers.
So we're going to see this inequality come back up in a minute when we talk about unsolved questions. But that is, of course, only one way that we might compose 2 knots together, just by eliminating one of the sticks and combining it in that manner. So if there are other methods that could potentially lead to lower stick numbers. We have bounds on the stick number. We know that it'll be at least as big as this. This lower bound is a fairly difficult thing to demonstrate, to show that it's true. It's one of the exercises with an asterisk on it, which I think many of us have come to dread at this point. But the book does give a hint: look straight down one edge and then count the crossings to obtain a bound on CK in terms of S of K, then invert the inequality. I took a stab at that and found it to be rather difficult. But the upper bound, on the other hand, is just briefly mentioned in the textbook as having been proven by a professor from Yokohama National University in Japan, whose name I will respectfully not try to pronounce. And we see that the upper bound is a much simpler formula, much simpler inequality. The stick number is less than or equal to 2 times the crossing number. So here are some bounds. So we can at least narrow down the stick number somewhat. And again, in some of the unsolved questions, we want to know, could we perhaps do better than these? So unsolved questions, I mentioned a moment ago, could we improve the inequality in exercise 1.37? Maybe making it -2 or -3. Again, the illustration that I showed over here with my sticks is just one way to compose 2 knots that are in the form of a stick knot. There could be perhaps other ways to do that might lower this by more than 1. So that's unsolved question number 1. Number 2 would be, does S of K change if we insist that all the sticks are the same length? Notice in my projection of the figure 8 knot and in the trefoil knot that's in the textbook, the sticks are not all the same length. So if we forced all of the sticks to be the same length, would it require more sticks for some knots? It's possible. It doesn't seem likely that the stick number would go down. It could possibly go up, and that's again one of those questions that we don't know the answer to yet. So in terms of applications, right? Like why are stick knots even relevant? Why are they in the textbook? Why do we care? And apparently, I did read through chapter 7. I didn't see a direct reference to stick knots, but you can see specifically in the sections on the synthetic chemistry in 7.2 that they're talking about trying to synthesize molecules, and there's only certain ways in which they will connect. And at the molecular level, there's not a lot of flexibility on how you can arrange various bonds, and so they act a lot more like sticks than like loops and elastic things like we've come to use in a lot of our knot drawings, right? Planar isotopies allow us to stretch things and move things around very flexibly, but in this chemical bond situation, things are not that elastic, they're not that stretchy. So the knots actually act a lot more like sticks than they do like our other knots. So that was the most direct application that, at least to me, that's what it appeared to be coming from chapter 7. So thank you for watching, and I hope you have a successful end to your semester.